So let's start with this ECG from the last video. So starting off with the rhythm, so we can see that it's irregular because there's an irregular R2R interval. We have 4 big squares, then 3 big squares, then 4 again. So it's irregular. And then we can calculate the rate by counting the number of QRS complexes on the 10-second strip and then timesing by 60. In this case, it's already calculated, it's 84 beats per minute. And then we can look to P waves. In this ECG, you can't actually see the P waves. There's no P waves in lead 2, which is normally the best place. Positive P waves you should have in lead 2, biphasic in V1, like that. And you should have negative in AVR, but we can't actually see any P waves at all. So we can't calculate the PR interval either. So we'll move on to the QRS, and so we can say that this is a wide complex rhythm, especially in V1. So we'll take the widest QRS complex, and it is greater than 120 milliseconds. So that is going to be a wide complex rhythm. What we're going to move on to is calculating the axis. I'm going to try and give you an easy way to say whether the axis is normal or not. And then we're going to go into how to actually calculate the axis. So first of all, let's think about the leads. So each one of these leads, and these are the limb leads, by the way, these are the leads that we'll use to calculate the axis. You don't use the precordial leads, which is V1 to V6. This is going in a different plane. We don't want to use these. So the next step is to calculate the axis. And some people have a little bit of difficulty in calculating the axis. I'm going to try and give you an easy way to say if the axis is normal or not. And then we're going to go about actually calculating it and giving it a number. So here you can see the limb leads, not the precordial leads. The precordial leads are these leads. We don't actually use the precordial leads in calculating the axis. We just use the limb leads. Each one of these leads takes a snapshot of the electrical impulse traveling in its direction. So say, for example, we have electrical impulse moving down this way, and we're going to have toward the electric. So now we're going to go about calculating the axis. A lot of people have difficulty with calculating the axis. I'm going to try and give you a quick way to say if the axis is normal or not, and then we're going to go about actually calculating it. So these are the limb leads. These are the leads that you use to calculate the axis. Each one is taking a snapshot of the electrical activity moving in its direction. So if the electrical activity is moving towards the lead, you're going to have a positive deflection. If it's moving away, you're going to have a negative deflection. And this is really important in calculating the axis. We don't use the precordial leads in calculating the axis V1 and V6. So each one of the leads that we just saw has a particular number attached to it. It's at a specific orientation. So we have lead 1 at 0 degrees, lead 2 at 60, lead 3 at 120, and then we have the other leads. So augmented vector, doesn't really matter, but AVR for right, AVL for left, and then we have AVF for feet. So each one of these leads will be assigned a number. And so here you can see that if the electrical impulse in the axis I like to think of is the large part, the majority of the electrical impulse is traveling towards a specific orientation, and that is the axis. So if the axis is traveling towards, let's say, lead 2 at 60, you're going to have a positive deflection. If it's traveling away from a lead, you're going to get a negative deflection, say an AVR in this example, at minus 150. Now let's move on to an example, and now I'm going to give you a quick way to say if the axis is normal or not. Now, if we look at lead 1, it's positive. The QRS is positive. If we look at lead AVF, it's also positive. We can actually say that this is a normal axis. The reason why we can do this is because here is the electrical impulse, and here we're going to see a big QRS complex. Everything in this half is going to show up as positive. If we're perfectly in the direction of the axis, then it's going to be a big positive, a big tall QRS wave. If we're over here, it's going to be a smaller QRS wave. Maybe in the middle, maybe somewhere in between. If we're on the opposite side, if we're in the opposite half, we're going to have a negative. The closer we get to the line, the smaller the negative is going to become, and then it's going to become positive. So in doing this, we can estimate that if lead 1 is positive, then the axis is going to be somewhere in its half. Conversely, if AVF is positive, I'm going to get another color out. If AVF is positive, then it's going to be, the axis is going to be somewhere in its half. Now we can see that we have to satisfy both halves, and we come up with this quadrant. So the axis is somewhere in this quadrant. So we're actually happy because that means it's a normal axis. A deviated axis would be greater than 90. So a rightward axis, a right axis deviation is greater than 90. And a left axis deviation is greater or less than, depending on how you want to look at it, minus 30. So it's not a perfect way because we're also not a perfect way of calculating the axis because we're also missing out this portion here. But we can definitely say that the axis is within 90 and definitely within minus 30. So the axis is normal. So if we see that lead 1 and AVF are both positive, then we can say the axis is normal and we can move on. Unfortunately, in this example, we don't have that. Lead 1 is positive, but AVF is negative. So we have to do something slightly different. What we actually have to do is look at a biphasic wave. So if the electrical impulse is moving towards a lead, such as here in the case of 1 and AVL, it's going to be positive. If it's moving away, it's going to be negative, such as lead 2, lead 3, and AVF. If it's actually perpendicular, so if the electrical impulse is perpendicular to the lead, you're going to have a biphasic wave. It's not always a perfectly biphasic wave. Sometimes it's just the closest to being a biphasic wave. So it might just be the smallest wave. But here we can see that this is a biphasic wave, and this is perpendicular to the electrical axis. So we have the diphasic wave at 150. Now from that number, what we have to do is add or subtract 90. In this case, we know that the axis is going towards lead 1 and AVL. So what we're going to do is we're going to add 90 and go clockwise over towards AVL. So that is going to be, so 90 off 150 is going to be, sorry, I got that wrong. It's going to be negative 60. I'm just going to illustrate that quickly again. So we have an isodiphasic wave at AVR over here. So that means that the axis is going to be either over here in the direction of lead 3 at 120 or over here in the direction of AVL at minus 30. We know because we can see that AVL was pretty positive and lead 1 was pretty positive. So we can bet that the axis is going to be in this direction. So what we're going to do is we're going to take the diphasic wave and we're going to add 90 in this direction. And what we come up with is an axis at minus 60. So there is left axis deviation. And so let's go to some of the causes of left axis deviation. So one of them is myocardial infarction. And this is true of both right axis deviation and left axis deviation. It depends on where the occlusive myocardial infarction is. Another cause of left axis deviation is left ventricular hypertrophy. You can also have fascicular blocks, bundle branch blocks. We'll come to them at a later date, hopefully. And hyperkalemia. Hyperkalemia is often called the great mimic, the great imitator. It can basically produce anything. And of course, a left axis deviation can also be a normal variant. It can actually be a normal variant in short and stout people. Conversely, a right axis deviation can be normal in tall and thin people. Unfortunately, I would be on the first example. Okay, so let's look at this example. Now, we look at lead 1, and we have a negative wave. We look at AVF, and we have a positive wave. So we need to calculate again. We need to calculate the axis. So now let's try and find that isodiphasic wave. Not in the precordials, but in the limb leads. So these are pretty big. These are pretty big voltages over here, so we're not going to do it there. Again, that's pretty negative. AVL is pretty negative. Again, actually, it's going to be, AVL is probably going to be our closest to an isodiphasic wave. It's a bit of a strange wave, but it's got a negative portion and a positive portion round about in equal parts. So we're going to take that as our isodiphasic wave. However, this time, the predominantly positive leads are actually going towards AVF 2 and 3. So instead of going clockwise from AVF, from 150, we're going to go anti-clockwise. And so we're going to add on 90 going in this direction. So this, if this is going to be 180, so that's 30 over there. Another 60 from 180. So we're going to be at 120. So 120 degrees. So that makes our axis perfectly in line with lead 3. And that pretty much correlates with what we see on the ECG. The tallest wave is lead 3. So there we have a right axis deviation because it's greater than 90. And now I'll show you some of the causes of right axis deviation. So again, a myocardial infarction just depends on the location. And there you can see pulmonary embolus. So this should underline how important it is to identify a deviated axis, especially a new onset deviated axis. So you have to rule out a PE, especially in the clinical context. Say if someone has chest pain, shortness of breath, a DVT, or maybe a malignancy, and you've got a new onset right axis deviation, you definitely want to rule out PE. Another example, right ventricular hypertrophy, say for example due to chronic pulmonary disease like COPD, and of course hyperkalemia, and also fascicular blocks and bundle branch blocks as well. So I'll leave you with this example. So go through it, calculate the rhythm, the rate, go to your P waves, your intervals, and then try and calculate the axis.